Hello and welcome. I am Dr. Anil Joshi. Welcomes you to my series Learn Radiology with Dr. Anil Joshi. Today's topic is based on MRI physics. MRI has got different sequences. Today's topic is based on the FLAIR, DWI and ADC. Before we go to the topic proper, let's know the acknowledgement, disclosures. Most of the material we have used in the illustrations are from our department. However, some of it has come from the net, which we have confirmed is royalty free. And most important thing is it is going to be used for teaching purposes. However, still we acknowledge with thanks from those we have got this material. With this, let's start going to the topic proper, learning of physics, that is particularly a sequence FLAIR. Why there are different sequences? It's very simple. If I give you a cross section of a abdomen, you will not be able to differentiate liver, spleen, kidney, spine unless there is a contrast between them. If everything is looking same as that of either of single color, then we cannot identify them. Now, to identify them of the different type, there has to be different grayscales allotted to them. Now, machine do not understand anatomical part. Machine understand only signals. From some it can give more signal, some it can give intermediate, and some it can give less signals. Now, based on that, we have designed a sequences where the signals are coming from a machine based on the magnetization and hydrogen ion, which are around 80% water is there in the body, it comes from them, so abundantly available. Based on that, tissue content of water and other things gives us a different type of contrasts, a different type of signals. There are different signals, different contrast and different sequences. Now, different sequences are concerned with either TR or TE. Now, let's see in the series details of all these. That is the magnetization, then radio frequency we apply. Radio frequency energy is same as that of the any other energy. Now, it is applied to the tissues. Tissues will react in different ways. Some will have faster recovery and some will have slow recovery. Depending on that, we image them. Now, out of these imaging, out of these sequences, today's topic is FLAIR. Let's get going to the topic. FLAIR is an important imaging technique that is used to suppress signals from the fluid in the body and improve the contrast between the fluid and surrounding tissues. It is particularly useful in detecting characterizing brain and spinal cord pathologies. Why? Because CSF spaces. If CSF spaces are also disturbing with same signal surrounding tissues, it will be difficult for us. So, we can suppress the CSF signals, and that is what is required. Now, in the brain, it helps to detect the parenchymal edema without glaring high signals from CSF. It can differentiate from them. To do this, we need to suppress the CSF signals. How to identify FLAIR? At first glance, FLAIR images appear similar to T1, that is CSF dark. Now, the best way to tell the two apart is to look at the gray white matter. T1 sequences will have gray matter being darker than white matter. T2 weighted sequences will have fluid attenuation or not will have white matter, darker than gray matter. So, which is darker? White matter darker, and which is less dark is gray matter. That's why T2 weighted sequences, whether the fluid attenuation or not, will have a white matter darker than the gray matter. The physics behind FLAIR MRI involves the use of an inversion recovery pulse sequence. In this sequence, a 180-degree rotational frequency is applied that is used to invert the magnetization of the protons in the tissues being imaged. This is followed by a decay or delay called as inversion recovery, that is TI, during which the photons are allowed to recover some of them of their longitudinal magnetization. Next, a 90-degree radio frequency pulse is used to excite the protons. Most of them are from water, and resulting signal is measured by MRI scanners. Because the magnetization of the fluid in the tissues such as cerebrospinal fluid has not fully recovered, signal is suppressed in the resulting images, resulting in improved contrast between the brain tissues and the cerebrospinal fluid. T1 weighted FLAIR. So let's go to some in details of the sequences. T1 weighted FLAIR, in this type of FLAIR MRI, the images contrast is primarily based on T1 relaxation properties. T1 weighted FLAIR is useful in visualization structures that have high lipid protein content such as the pituitary gland, white matter and cortical bones. T2 weighted FLAIR, in this type of FLAIR MRI, the images contrast is primarily based on T2 relaxation properties. T2 weighted FLAIR is useful in visualizing structures that have a high water content such as CSF, edema and white matter lesions. The two difference between T1 and T2 FLAIR is the type of tissue contrast that is emphasized. T1 weighted FLAIR is useful in imaging lesions that have low water content such as calcification, hemorrhages or some tumors. T2 weighted FLAIR is better for imaging lesions that have high water content such as edema or inflammatory process. The T1 value used in FLAIR depends on the manufacturer and strength of the MRI machine being used as well as desired imaging parameters. So these are set by the manufacturers. Typically the T1 value for the FLAIR is set to BE, and in the range from the 2300 to 2500 milliseconds on most MRI machines. However, it do differ. This MRI sequence T2 FLAIR is designed to suppress the signal from the fluids such as cerebrospinal fluid and to highlight an abnormalities that would otherwise be observed by the they will be obscured by high signals of CSF in T2 FLAIR. So the lesion will be seen better. A long TR, that is a time repetition, and a long TE, that is time to echo, are used along with the inversion pulse, which suppresses the signals from fluid. The resulting image highlights white matter lesion, infarcts and other pathologies, making it a useful diagnostic tool in neuroimaging. Now, tissue appearance in T2 FLAIR images. Cerebrospinal fluid appears dark due to selective suppression of fluid signals in FLAIR MRI. Gray matter appears as hyper-intense bright on T2 FLAIR due to high water content and unique microstructures. White matter are hyper-intense bright on T2 FLAIR due to its high water content. Ligaments are hypo-intense dark on T2 FLAIR due to their low water content. So if you know a water content of the tissue, you can know how they will appear, or in other words, it is identification easy if you go by this way. Muscles are hyper-intense and bright on T2 FLAIR due to high water content. Edema is bright, it is just a water due to increased water content, and blood products appear dark due to presence of iron, which shortens the T2 relaxation. Now, tissue appearances in T2 FLAIR images. Bones appear as the hypointense dark on T2 due to low water content. Blood vessel in general, blood vessels have a low signal intensity on FLAIR, similar to their appearance on T2 images. However, in some cases, blood vessel may appear hyperintense on FLAIR due to slow flow of their factors. Now, spinal cord appear hyperintense or bright due to suppression of CSF signals. The surrounding cerebrospinal fluid CSF and subarachnoid space appear dark, providing better visualization of the spinal cord tissues. Now let's go do DWI, a favorite sequence of stroke. Those who are dealing with stroke, those who want to detect the early stroke, those who want to detect best possible results for thrombolytic agents, for them DWI is the most favorite sequence. So also for a radiologist, because the information it gives in a shorter time is tremendous. DWI refers to what is better termed as isotropic T2 weighted map, as it represents the combination of actual diffusion values of T2 signal. It's a relatively low resolution image showing following appearances. At first glance you will not or may not like the image because it doesn't look that aesthetically good, but the information it gives, yes, that is why we prefer this sequence, and that is why it is a favorite sequence of stroke clinicians. Now gray matter appear intermediate signal, that is gray. White matter slightly hypointense compared to gray. CSF low signal, that is black. Fat little signal due to paucity of water. Other soft tissues like intermediate signals intensity are given by actual pathology like ischemic stroke, cellular tumor. Then pus usually appears as an increased signal denoting restricted diffusion. What happens when a tissue suffers ischemia? It becomes swollen, and there is always an exchange of water going on between extracellular compartment and the tissues. So once the tissue swells, this exchange of hydrogen, that is the water which is going on between the tissues and the extracellular compartment, gets blocked. That's why the word restricted diffusion. However, and because there is a complexity of the image derived from T2 signal, some tissues that are bright on T2 will appear bright on DWI images without they being abnormal restricted diffusion. So we have got methods to differentiate them. We would like DWI images to be entirely appear like DWI. No mixing, no artifact, no gray zones. Means we would only see the result of the diffuse or diffusion edema, and not other properties of the tissues other than edema. For this, TR is long in order to reduce T1 effect and improve the signals, but the insertion of the diffusion gradient after 180 pulse necessitate a longer T. Therefore, TWI images are also T2 is weighted to some extent. Now, there is a very important point to note. Lesions may be bright on DWI from T2 effect alone. This is known as T2 shine through, and lesions that restricted diffusion and longer T2 relaxes will appear very bright. Therefore, T is kept as short as possible in these sequences. Now practical point. How does one acquire a diffusion weighted image? A typical DWI image sequence are spin echo sequence with 90 and 180 degrees pulse. However, ways to perform DWI are being developed. Many of them do not use spin echo sequences. The diffusion gradient are turned on before their 180 degrees pulse. They are thus both positive gradient because the 180 degree pulse serves to reserve the effect of the second pulse. Then what are prerequisite? DWI sequence need to be extremely fast in order to eliminate any motion within the body parts. Since the entire purpose of the DWI sequence is to measure value closer to zero, movement of the water molecules, our images will be completely destroyed by macroscopic motions. For a long time, A faster sequence available was echo-planar imaging (EPI), and virtually all the currently used DWI sequences use EPI. Now, reasons for fat creation problems in DWI. First, it is bright on DWI images because of the fat molecules do not move very fast. Fat molecules do not move very fast. They are relatively restricted fat signals which might obscure the lesion. Secondly, the chemical shift artifacts of the first kind is much exaggerated by echo-planar imaging (EPI), often around 10 pixels of a shift. This is because phase shift accumulate across the signal shot of the EPI sequences. The fat from the subcutaneous tissues could obscure lesions in the brain and liver. For both of these reasons, homogeneous fat suppression is necessary for DWI images. Diffuse weighted imaging access the ease with which the water molecule move around within the tissues are picked or imaged, mostly representing fluid within the extracellular tissues. Now, I had told you fluid is there extracellularly, fluid is there intracellularly, and there is free exchange going on in these two, and gives inside cellularity, that is of the tumor, information, and cell swelling, that is edema. Both can be seen or detected by DWI sequence. Now, what are the fluid signal intensities of different tissues? Urine, CSF, there is no restriction to diffusion. Soft tissues, muscles, intermediate diffusion. Fat, little signals due to paucity of water. Typically, there will be 3 sets of images when diffusion weighted images is performed: DWI, ADC, and B0 images. Now, let us come to ADC, also called as apparent diffusion coefficient. The diffusion coefficient we measure with MRI represented average of the entire voxel of each direction of the diffusion. Therefore, we use the word apparent. Apparent is used because of that to describe the values we calculate. The signals of a particular tissue decreases exponentially with increasing B value. Given an apparent diffuse coefficient D, the signal intensity is calculated by this equation. If we acquire at least 2 DWI sequences with different B values, we can plug them into an equation to solve the D. Typically, 3 different B values are used to improve noise, that is 40, 400 and 800. We can take the log of intensity to linearize the graph and then use linear regression to get a best fit D by plotting D for each pixel. Thus, we can obtain ADC images, sometimes called as ADC map. Apparent diffusion coefficient are images representing the actual diffusion values of the tissues without T2 effect. They are therefore much more useful and objective measures of the diffuse values that can be obtained. However, the images are much less pretty to look at. As I told you, they are grainy. They appear basically as the grayscale inverted DWI images. They are relatively low resolution images with the following appearances: gray matter, intermediate intensity, white matter, slightly hyper intense, CSF, high signals white, fat, little signal due to paucity of water, then other soft tissues, intermediate signals, that is the gray, and acute pathologies. Yes, this is what we want. Ischemia, strokes, cellular tumor, pus, as they appear, they are important. they appear as a decreased signal denoting restricted diffusion. B is equal to 0. If we see these, don't worry. They are only used to calculate ADC. They are essentially T2 weighted images with a bit of susceptibility effect. Areas of diffusion restriction will look, or they will lose the least signals on the high B values because of their protons are not moving. That's why B is kept as 0. The scope of the line on the DWI plot will be fat, and thus the ADC value will be smaller. Therefore, it will look dark. On the other hand, areas of fast diffusion will lose its most signals as B values increases, giving a large slope and a bright pixel on the ADC map. That is, brightness of DWI images related to the underlying T2 signal in the tissues only affects the initial portion of the point in the DWI plot. It does not affect the slope. Thus, the ADC images is independent of T2 shine through. It reflects diffusion and diffusion alone. Clinical limitations. In a typical DWI image, a bright abnormalities are much easier to see than the dark abnormalities. People have developed several strategies to transform the ADC image into a bright, that is a bad map, or for example, the exponential ADC EADC map takes the exponential on the ADC values, leading to an inverted scale more similar to that of DWI, but again eliminating T2 shine through effect. Another important reason to use DWI images is that because the ADC images relies on several DWI images, it is inherently more susceptible for artifact than individual images. Finally, for many abnormalities, they not only restrict diffusion but are bright on T2. Thus, we can actually take advantage of the T2 shine through effect to make lesions more conspicuous than confirm them on diffuse restriction on ADC map. With that, we are coming to end of lecture. I thank you for giving me your valuable time. Do visit our website, our YouTube channel. There are a lot of lectures similar to those, giving many more detail on many more topics. Thank you, goodbye, and take care. See you again in next lecture.